So, you guys ready? I hope you have tried alone, but if you didn't have time and you just want to follow along, that's fine too. Although I do think, I'll insist a little bit, it's good practice for an independent activity and for the exam that's coming on, okay? But if you want to follow along one more time, that's okay as well. So, to answer the question, basically she wants to know, the cousin wants to know, are there differences between these categories if we're looking at top salaries? And we have a variable for that. We have the 75th percentile salary as well. So, process. First, check assumptions. Number one, so let me go to the one with no answers. And I'll save this. Let me pause for 1 second. Now we can start working on problem 2. So the first thing is to check assumptions. I wrote the 4 assumptions there. For the independent activity, you're going to have to write those assumptions. Is it numerical data? Yep. Independence of observations? Yep. Random sampling, less than 10% of population size. Distribution is slightly skewed, let's say slightly skewed, but within acceptable range. So we will move forward. Homogeneity of variance can be assumed. But now, question 5 is that you need to provide support for 3 and 4. So the first step is to get the range of the variable that you want. And for that, we need the data set name, which is data cropped, that only contains those 3 majors, remember? And we want to look at the variable this time, 75th percentile, not 5th percentile, to construct our histogram, and that goes from 41,000 to 125,000. And so how would you change things? Well, you go there. Let's get the base code for a histogram with the facets. Where is it? It's right here. So we'll just get this, copy and paste. The easiest way to work the code. What do we have to change? Name of the data set? Variable? Yep, we need to do that. That's 75th percentile. The range, we do need to change that. Let's go from 40,000 this time to 30,000. We can go by 2, leave that and see how that goes. And we still want major category here. And then we can say top salary. By category, the source is the same, so we can just run it and take a look at what comes out. This will probably don't get much better than this, even if we make steps less refined. Let's look. Still not great, but I do think if we make it less precise, the binning less, the bin width higher, it does improve a little bit, but because the data sets are so small, it will never be nice and smooth for us to look at the distribution. So as I mentioned, for small sample sizes, this is typically the case, but it's sufficient for us to see that it's definitely not a flat distribution, right? So every single, the likelihood of every single value is the same. A uniform distribution, it's not. So box plots are a good way to kind of gauge the distributions in a way that's a bit less cumbersome when you have less, smaller data sets. So let's get the code for the box plot. So you go up, oh, here's a box plot. So you can grab this code. Note that I'm copying just the code because I already have the box. You go back down here, you copy, and then your job is to look at the code and say, what do I have to change? Data set? Nope, same data set. Just variable, that's yes. An explanatory variable is exactly the same, so that's all I need to do. And we can look and see, the distribution. Engineering looks pretty good here and here because the median is not in the middle of the box. It looks less you really need to check the numbers because, it suggests some skewness. So you should get descriptives for that. So let's get numeric descriptives of skew and pickedness, and also compare the mean and the median. So let's see where we get those descriptives when we're checking. The describe by, that's the one you want. That's a function of the psych package. Let's go back there. Back here, so let's get descriptives. I copy and paste the code that I need. Remember, the first input is actually the data that you want to describe. And we don't want the 5th percentile this time because we want top salary, so we have to change that. The second input is the category that you want the breakout of. So that's major category. So here, the first output is computers and mathematics. The second is engineering. The third is physical science. If we look, mean and median are pretty close. Values of skew and kurtosis close to 0. Again, mean and median really close. And values of kurtosis, marginal there. And skew, so still okay. Mean and median, again, less close than the others, but not bad. I mean, it's not changing even the interpretation of the salary, right? It's close enough. And skew and kurtosis are not looking too bad, right? Skew, nice, and kurtosis still pretty close to true. So median, mean at close in magnitude, skew and kurtosis within the expected range, or just slightly increased. Not considerable deviation from normal to worry us because most things are falling into place in terms of the numerics. So we'll move on. Homogeneity of variance. We are testing the hypothesis that there are equal variances across major categories for this new variable, P75th. And the alternative is that variance is different across at least 2 levels. So we need the code for the Levene test. Let's grab it up here. I'm going back and forth because this is literally the exercise that you have to do. Here's where we tested the hypothesis for this other analysis that looks like this one. So we just grab the code, copy and paste, and come back here and do it. So we can assume equal variances. So we're good. So what can you conclude here? The conclusion is exactly that you keep the null hypothesis and you assume, it's fine to assume that, that the variances are homogeneous across the different groups. Now, descriptive statistics, you need to get numerics, mean, standard deviation, standard error, confidence interval, and you need to plot the data, right? So let's get stuff for that. Let's first get the numerics. So here we go to descriptive statistics. Here, numeric summaries. Let's grab this and see what it is that we need to change for the numeric summaries. So I'm copying and pasting. So I want R to open data crop. Keep it open, look at the data crop and group by major category, keep the grouping and then summarize getting N. The mean, but not the mean of P5th, the mean of P75th. The standard deviation, again, not of P5th, but of P75th. Here, I don't need the name of the variable because I set up these two. There's nothing that I need to modify in this formula. The CI confidence interval, 95% interval for lower and upper margins. I don't need to modify anything either because the name of the variable doesn't show up because I have a formula there that uses this one, kind of like this. So the only things I need to modify in this code is the name of the data set. In this case, I didn't because the new variable is inside that same data set. You need to modify what is your explanatory variable. In this case, I didn't modify because it's the same. And you need to modify the value, the names of the variables for mean and standard deviation. The rest is just based on that. So if you plot, you have your descriptives, the numeric summaries here. And again, the top salaries for engineering majors still higher than the top salary of computers and majors in computers and mathematics and majors in physical science. The question is whether this difference can be expected if just chance was at play, right? But before we go there to inferential statistics, let's do the plot to illustrate this better. Let's get the code for the plot. Where do I have my bar plot before? Ah, here. Where's the code? Right there. And then, you change what you need to change. Right there. So here, again, this one is pretty easy because that's all you need to change. Just the name of the variable, which for the independent activity will be the same. Oh, I'm lying because you have a new data set. So you have to change the data set as well. So if you do that, you get your plot. So again, engineering is up here. You note that the errors are a bit higher. So whether the differences will be significant, that's a different thing. So now we'll run inferential statistics. And the null hypothesis is that the three means are the same. And the alternative hypothesis is that at least one pair of means is different. So let's run the ANOVA and see what's going on. Let's get the ANOVA piece. See, this is the base code to ANOVA. You grab it there, all of it, and you bring to where you need to do it. There. What decision should we make with respect to the null hypothesis? The probability is less than 0.05 for me to get this F value or larger, given the degrees of freedom at hand. So we should reject the null, right? Let's look at the key just so I can copy things and I don't waste your time typing things out. And in the context of data, we can say that the top salaries individuals get are related to their major category. We don't know, however, which pair of majors are different from each other. Major categories are different from each other. So we need to do follow-up comparisons. As I said, it would be fine in this case, desirable in this case, to run an LSD because we only have 3 comparisons and all of the 3 comparisons are pre-planned because it's driven by our question. We need to know all of these differences. So you can run here the features protected t-test as a follow-up. And if you want to practice, you can also run the Tukey's test and you see what happens when we do both. So let's start with the LSD, and I'll show you a twist I actually discovered to make it simpler. That's Monferroni, that's LSD. So let's get the base code for LSD. As we said before, we need our explanatory variable here is the same. We need our response variable, which is different, so I'm adapting. Data set is the same. We pass the model as input. The explanatory variable needs to come here again. But what we don't need to say anything about is these two. You can simplify. You can do here. because actually the default values for these two inputs can be taken out of the LM model. So you can delete this, makes it even simpler. You don't need to go back to the ANOVA table to get those. So please use this as your base model. It's fine if you use the other, but this one is just simpler. You don't have to go back to the ANOVA table. And if you click, we're still in the same situation. Engineering, greater top salaries than computers, and engineering is also better top salaries than physical science, but these two are not different. Okay, now note that if you happen to run Tukey test, which is more conservative, remember it's not as bad as Bonferroni, but it's more conservative. Let's watch what happens. Let's get Tukey. Tukey. There. We have to change just this because that's the same. Data is the same. Independent variable that we want to partition is the same. And when we look, we can see that we have only marginal differences between engineering and computers when you do more stringent corrections for repeated comparisons. Now, in this case, as I said, we have a reason to run LSD, so we could go with that. But just know how when you get more stringent, it becomes harder to find the difference. So you need to have a justification for your choice of follow-up analysis because of that. And those choices need to be a priori. So you can't run two and say, oh, because that one was significant, let me go with that. If we had more comparisons than 3, and they were not planned and justified, they were just exploratory, we would not be doing the right thing running LSD. Let me pause here and say that it's funny that I said it would not be the right thing to do. In statistics, that's hard to say. I would say, I think the most precise thing I should say is that it's not the most conservative thing to do. Okay, so, but the important thing is that you should have your justification, and you should look critically at the justification of authors of papers that you read when they are reporting their results. So let's look at decisions and let's use the LSD results. The one-way ANOVA supported a decision to reject the null hypothesis that the top salary was equal across all 3 major categories under analysis. Post-hoc analysis indicate we should reject H1 and the null hypothesis 1 and the null hypothesis 2, but not the null hypothesis 3, because it's just the engineering salary, the top engineering salaries that were higher than the salaries of the other 2 major categories, but physical science and computer and mathematics are not different from each other, so we can't reject H3. Let me change here. It's good that I go over this because then I find my typos and stuff. Okay. Interpretation. So when I ask for decision in the exam or independent activity, you can be blunt. Reject this, didn't reject that, done. Interpretation is more, how would you say this to somebody that is that doesn't understand statistical jargon, that just wants to know about the question? How would you write conceptually about it in the context of the initial question, okay? So it's a bit more conceptual when I talk about interpretation. And note that I'm doing my best to avoid statistical jargon that people will tend not to understand. So data provides evidence. You can tell your cousin that the data provides evidence that top salaries of recent graduates majored in engineering, physical science, and computer and mathematics also differ. However, majors were compared pairwise. Differences were not so robust. And the reason I'm saying this is because they even went away when we became a little more stringent. In particular, the 75th salary of engineering graduates, which varies from $64,283 a year to $76,613 a year. with 95% confidence is significantly higher than the salary of physical science and computer and mathematics majors. The salary of physical science majors range from 52,000 to 64 more or less, and the salary of computer and mathematics majors range from 45 to 69. So when I come back, I'll talk to you and give you a little introduction to the homework, and then we'll be done for the day. Okay? See you soon. Bye-bye.